know that the non-zero vectors of a matrix in row echelon form are basically independent, linearly independent from each other. So remember that we went over multiple examples for you. I just wrote down one example, so when I'm writing the general form of rows and columns, you can associate those to the matrix that you saw before. So suppose you have a matrix with entries Aij, like this scenario, this case here. A, B, A, M by N matrix. In this case, you have a 4 by 4 matrix, right? We're going to write this matrix in row echelon form. Suppose after reducing the rows, we have non-zero vectors representing by R1, R2, and Rk for the original matrix, all right? These can be written as R1 equals to the very first element, E sub 1 and 1. And then you have the rest of the elements, you have the rest of the entries. E1 and P, for example, then you have E1 and Q, and the rest of the elements here that you have. So comma to separate these as well. This is R1. The second one can be written as you can see, you have a 0, then, so this might be shifted. It might not be like this, written nicely. So you have a 0, might be more zeros involved. Then you have E2P, the rest of the elements, E2Q, and more. You can continue this process. R sub 3 can be written as 0 with some more zeros. You don't know how many zeros do you have. So we're just basically writing zeros. And 0, E3Q, and the rest of the entries. Let's continue the process. Well, what's happening here? We are denoting the leading coefficients. E11 is the leading coefficient of the first vector, which in this case is just 1. Then you have the leading coefficient for the second vector, which is E2P. Again, you don't know how many zeros you might end up here. E2P, leading coefficient of the second vector. Then you have E3P, the leading coefficient for the third one, and you continue this process. So what's happening here? If I write down C1 R1 plus C2 R2 plus CK RK equal to 0, basically writing the linear combination of the non-zero vectors and set it equal to 0. If they are linearly independent from each other, you need to be able to justify that C1, C2, and CK are 0. Let's take a look at this. Here you have C1 R1, which is basically written as C1 E11 equal to 0. Well, E11 is not 0, all right? So C1 must be 0. What about this guy here? You're basically multiplying C2 and E2P equal to 0, the leading coefficient. So basically we are saying that C2 must be equal to 0. Okay, continue this process. Do the multiplication. C sub k and R sub k. Ck must be equal to 0. So the rows are linearly independent. I have the same process here. C1, R1. C1, 1, 0, 5 over 9, 2 over 9, plus C2, 0, 1, negative 4 over 9, 2 over 9, plus C3, C4, they are not included because we are just working with non-zero vectors. So set it equal to 0. So you're basically saying that C1 plus C2 is equal to 0, but the C2 has coefficient 0. C1 plus 0. C2 is equal to 0, so C1 must be 0. Now here you have 0, C1 plus C2 equal to 0. So basically C2 is equal to 0. And then for the rest of them, since you already have C1, C2 equal to 0, these guys needs to be 0 to make the sum equal to 0. Here you have 5 over 9 C1 minus 4 over 9 C2 equal to 0. Basically, you are saying that if I multiply by 9, you have 5 C1 minus 4 C2 equal to 0. From the last equation, you have 2 over 9 C1 plus 2 over 9 C2 equal to 0, or C1 plus C2 equal to 0. So basically saying that C1 is equal to negative C2. And if you substitute it over here, this guy representing that C2 is 0. So basically C1 is equal to 0. So you can just take a look at one example and make sure you understand every step before understanding the proof and justifying the proof for yourself.